Good evening, everyone. So, today I'll be discussing the topic Boolean functions and canonical forms. Let us begin with the topic. So, in this slide, I have given all the possible functions of two Boolean variables x and y. So, these are the four possible combinations of x and y 0, 0, 0, 1, 1, 0, and 1, 1. So, this can have 16 possible functions from f0 to f15. So now let us look at the expressions for all these variables. So for f0, it is always 0. So f0 can be written as simply 0. Considering f1 now, in f1 we have a 1 where x is 1 and y is also 1. So f1 can be written as x and y. Now coming to f2, here there is a 1 where x is 1 and y is 0. So x and y complement. Similarly for f3, we have two ones, and the first one is where x is 1 and y is 0. So this term gives us x y complement, and the second term gives us x y, x also 1 and y also 1. So similarly we can write for all the other uh, functions also. f4 has a single term, f5 has two terms, f6 also has two terms, f7 has three terms, f8 has a single term, f9 has two terms, f10 also has two terms, f11 has these three terms, f12 has these two terms, f13 has these two terms and this term, so total of three terms. f14 has these first three terms 1, and f15 is always 1. So we can also say x naught y naught plus x naught y plus x y naught plus xy. We can also simplify this as 1. Now there is also a scope for simplifying many other expressions. For example, this f3 expression is nothing but x. So we can take x common in this and we get x into y complement plus y, which is x. Similarly, we have here 1 1 0 0 f12. F12 is x complement, and we also have uh, this is y complement, right? F10 is y complement. So we can take y complement common in this and we get y complement into x complement plus x, which is nothing but y complement. So we can simplify all many of these terms and get a simpler expression using less number of logic gates. Now let us see what are min terms and sum of product form for denoting a Boolean function. So now I am considering three variables x, y and z, and here we have written all the possible combinations of x, y and z. Now in min-term form, this x is 0, y is 0 and z is 0. So for the literals which are 0, they are complemented in the min-term, and the literals which are written as 1 are present in the uncomplemented form. So for all zeros we have x complement, y complement, z complement. Where z is 1, z is not complemented. Where y is 1, y is not complemented. And as x and z are 0, x and z are complemented. So we use this small letter m for the designation, and we use m0 to m7 for denoting the minterms. And suppose we had four variables here, then we would have m0 to M15 minterms. Now let us consider an example for the sum of product form. So I have taken a function of xyz. This is an arbitrary function of xyz, and let us see what is the sum of product form for this. So here we have 1 in this position. This is the position for m0. So we write x complement, y complement, z complement. And coming to the next one, we write x complement, y, z complement. Then the next one is x, y complement, z. And for the next one, we have x, y, and z complemented. So this is the sum of product form for this particular function. Here we have 4 terms, as many as the ones are there in this function. So basically what are we doing? So suppose for this term, x should be 1, y should be 1, and z complement should be 1 to get a 1 in this place. And for f to be 1, either this condition should be true, or this condition should be true, or this particular condition should be true, or this condition should be true. So if any of these 4 conditions are true, then f will be 1. So we are basically writing the condition for f to be 1. Now we can also write this expression using the designation. So this is m0, this is m2, this is m5, and this one is m6. And another way to write this same thing is summation of m0, m2, m5, m6. Now in similarly, we will discuss max terms and product of sum form. So in this form what we have is, there is a slight difference in this. So where we have all zeros, all of the terms are present in uncomplemented form. So a 0 is written without a complement, and a 1 is written with a complement, right? So the designation used for these max terms is a capital M, and just like min terms, for this case of 3 variables, we have the designation ranging from capital M0 to capital M7. And suppose if we had 4 variables, then we would have capital M0 to capital M15, that is 16 max terms. So we have for all zeros x plus y plus z, and where all the terms are, all the literals are 1, we have all the variables complemented. Now let us consider an example for this. So I have taken the same example which I took for minterms and sum of product form. So let us write the expression for this. So where now what we will do in this is, first of all we will see where we have a 0 in this function. So we have a 0 in this position. So for this we have this particular term 0 0 1 x plus y plus z complement. For the next 0 we have 0 1 1. 0 1 1 can be written as x plus y complement plus z complement. Then the next 0, x is 1, y is 0, and z is 0. So this is this particular term x complement plus y plus z. And for the last 0, x is 1, y is 1, and z is also 1. So we can write it x complement plus y complement plus z complement. Another way to write this is using the designation, and that is, this is m1, this is m3, this is m4, and this is m7. And this dot denotes multiplication. Multiplication here stands for AND, the AND logic. And just like we use sigma for the min terms and sum of product form, for max terms and product of sum form, we will be using this uh, symbol pi, capital pi, right? M1, M3, M4 and M7 product. Now you may think that how did we get this product of some form, which is not very obvious, that how you can think about it, that why are we choosing zeros and not the ones like we did in the sum of product form. So what happens is, suppose first we take the complement of the original function. So wherever there were ones in this function, I have written a 0, and wherever there was a 0, I have written a 1. So this is f complement, and I have written f complement in the sum of product form. Now if I take the complement of this again, I'll get the original f function, right? And this complement of f complement, we can use De Morgan's theorem. If we apply De Morgan's theorem in this, we get this becomes this and changes to or, and all the complements, all the literals get complemented. So x complement gets removed, y complement, uh, the complement gets removed, and z gets complemented. Similarly, this or will get converted to and these, the and in between x complement y and z gets converted to or, and x was complemented, x becomes uncomplemented, y and z which were not complemented have become complemented in this. Similarly for the other two terms. So this we have done using the generalized form of De Morgan's theorem, which we can call generalized form of De Morgan theorem states that the complement of a function is obtained by interchanging and or operators and complementing each literal. So we have complemented each literal in this. X complement became x, y complement became y, z became z complement. We took complement of all these literals, and instead of these or symbols we have replaced by and symbols, and these and symbols we have replaced by or symbols, right? So let us have a relook at the expression that we have derived for the sum of product forms. So earlier we had derived this particular expression for the sum of product form, and we said that all these terms x bar yz, x bar yz bar, x y bar z, x y z bar, all these are known as min terms, and these can be written as m0, m2, m5 and m6, or in the other way as summation of m0, m2, m5, m6. So we can also simplify this particular expression, because we notice that in both these terms this x bar and z bar is common, and if we take it common, then what we are left with is y bar or y. So we know that y bar or y will always be true, right? So we can replace this by 1 and we get this expression. In this expression, we can remove 1, we need not write 1 here, and we get this expression x bar z bar plus xy bar z plus xy z bar. So, is this expression a sum of product form, right? This is also a sum of product form. So, is the above a canonical form? Yes. Is this a sum of product? Certainly, because this contains all the terms in this contain all the literals, whether in complemented form or in uncomplemented form, but x, y, z all are present in all the terms. So this is a canonical form, and we are taking the product first in all the terms, and then we are taking the sum. So this is a sum of product as well. But in this, this is not a canonical form because in the resultant expression in this particular term y is missing. So as y is not present in this particular term, we cannot say that this is canonical form. So this is not a canonical form, but is this a sum of product form? So yes, this is also a sum of product form because here we have a product, here also we have a product, here also we have a product, and we have the sum of all these three products. So this is not a canonical form, but this is still a sum of product form, while this is the canonical sum of product form. In the similar manner, we also have canonical product of some form and non-canonical product of some form. So if any of the variables are missing in the product of some form, then it is still product of some form, but it is not the canonical product of some form, right? Now let us consider some previous year gate questions. So we are given this Boolean circuit and we need to tell which expression corresponds to this circuit. So I have drawn the truth table for this. So the expression that we need to get for this is for this gate we need b complement c. Here we will be getting b complement c, and that we are taking or with a. So the overall expression for z is a or with b complement and c. This is the overall expression. So we get b complement c first, and then we see the or of a and b complement c. So we notice that we have one at M1, one at M4, M5, M6 and M7. So this option is represented in 1, 4, 5, 6, 7, that is option A. So A is the correct answer of this question. So in this question, we need to find out the number of minterms after minimizing this Boolean expression. So in this Boolean expression, suppose I do not consider this complement sign, then I will get the complement of this Boolean expression. So suppose this Boolean expression is f, I will get f complement if I do not consider this complement symbol. So let us find out f complement first. So wherever we have that literal d as 0, we can put a 1 in f complement. So d is here, d is 0, here d is 0, here d is 0. So we'll put a 1 in f complement wherever d is 0. Now we'll find out those places where a is 1 and b is 0. So a is 1 here and b is 0. A is 1 here and b is 0. So we'll mark these places also. Then we'll find out those places where a is 0 and c is 1. So a is 0 and c is 1 here. Here also uh, a is so we'll mark all these places. Here also a is 0 and c is 1. So we'll mark these places. Now we'll mark those places where a is 1, c is 0 and d is 1. So a is 1 below this particular position, c is 0 uh, here, right? So a is 1, c is 0 and d is 1. So we'll mark this position. Then we'll mark those positions where a is 0, c is 0 and d is 1. So this is one such position, a is 0, c is 0 and d is 1. The next such position is this, a is 0, c is 0 and d is 1. So we'll mark this position. Now let us take the complement of this f complement to get back the original f. So in this f, we need to write the uh, min-term form. Min-term form, that is the uh, sum of product form. So if we want to write f in sum of product form, we'll write the min-term corresponding to this one, that is a, b, c, d. So f is equal to a, b, c, d. So we have only one min-term, right? So the answer to this question is one min-term. So thank you for watching today's session. We'll continue with more questions in the next session, and we'll also discuss some more topics. Thank you.